This is our GATE 4.5 report Rezo video for Team 50, the Kinetic Dispersion Testing Project. The team, myself, Brent Tardine, Griffin Miller, Trey Stroop, Dalton Weber, and Juliana Reyes. For this problem, we're looking to see what can be done to create a repeatable experiment for the testing and force for the testing of force distributed by a bullet in soft tissue. U.S. manufacturers and testing facilities need a more precise and repeatable method for testing bullet impacts. Existing techniques fall short of achieving kinetic energy dispersion data. Work will include creation of an apparatus containing accelerometers to map bullet impact data as energy is dispersed through the ballistics gel.
The scope of the work and methods for this ballistic dispersion tester is to develop a device to measure kinetic energy dispersion in ballistics gelatin. The key feature of this experiment are the accelerometers, of which are integrated into the gelatin to capture the impact data that is dispersed through the gel as the bullet travels through it. There are three phases of this project: the research and conceptual design phase, the prototyping and sensor integration phase, and the testing with various ammunition types for validation phase. The collaboration of both vertical and horizontal between peers and faculty across multiple Purdue University campuses helps to achieve what the scope of the project can be. And then the final outcome we're aiming for is a fully functioning testing apparatus for military and munitions manufacturers. The methods we will go about to complete this scope is by obtaining testing data using small-scale impacts with ball bearings and rebar, which will eventually be scaled up to real-world validation across multiple ammunition types. The implementation guide are step-by-step instructions for field deployment, if needed, and the technical report as a result of this experiment would be a comprehensive documentation of research, development, and testing.
So as we're all certainly aware, there's nothing really out there on the market for this type of device right now, but a quick overview of the state of the art reveals many strengths and weaknesses. We looked at things like ballistic gel torsos, ballistic gel limbs, things that focus on bulletproof vests, high-tech imaging systems for bullet impacts, to get a better idea of this particular type of device and prototype. The strengths that we found were typically were realistic human simulations. They had good material adaptability. Some of those things that, like the bulletproof vests, targeted the protective gear, which is what we're shooting for, to improve. The advanced measurement techniques and applicability beyond ballistics. Some of the weaknesses that we found were some of those things were limited in scope. A lot of those things were really only for extremities, such as arms or legs, or just the center mass on the torso. Some relied entirely on the material, such as reusable ballistics gel, or had to be particularly calibrated ballistics gel. The complexity and sub requirements, obviously, when you're talking about highly advanced things, they're going to be very difficult to implement in the field. And then a lot of these things are very high cost. Something that we've been able to take advantage of is the low cost of our prototype, and environmental sensitivity plays a lot into the state of the art as well. We've been able to eliminate on it.
So for our system sub solution, we're looking at two different sensor types, first being our force gauges. These at the time being do not produce a precise enough result for what we're looking for when they are not directly in the path of projectile impact. So we're also testing accelerometers, which can read the oscillations in the gelatin, giving us a more precise view of how the kinetic energy disperses through the gelatin itself as it's expanding and contracting during a bullet impact.
So as Brent just covered, we kind of had two forms of testing that we performed already. The first one was with our pressure sensors and the bearing drop test. That is the top graph here. And what we can see here is a progression of first dropping with a very thin layer of gel and directly on top of the sensor. The one spike was just us validating the sensor by pressing down on it physically with our hands. But very quickly, as we applied more and more layers, the results that the sensor gave got so small that we weren't able to get a representative data point, especially as a bullet travels through a larger block of gel. So we moved on to the accelerometer tests, which you can see in the second graph. And the good thing about the accelerometers is due to the oscillation of the gel itself, we are able to get a very nice visualization that we can then apply to some mathematical models to get the actual kinetic dispersion.